Hello, my name is Aida Colon and I am a PhD student at Columbia University. Last semester, I had the opportunity to take a course instructed by Professor Peter Kinget, where we were able to propose an idea for an integrated circuit and later test it out. I would now like to present the results for the 6350 course where I chose to work on oscillators. We use oscillators on a wide variety of applications, but these can be summarized into two main branches: timing references for clocking in digital systems, and signal generators for communication systems, mixers, and VCOs. Before going into oscillators, we need to understand what resonators are. A resonator is a device that naturally oscillates at a given frequency. This frequency at which its electrical properties change depends on its mechanical or electromagnetic characteristics, and it's called the resonance frequency. There are two types of resonators: electrical, which include inductors and capacitors, LC for short, and mechanical, including crystal oscillators and microelectromechanical systems, or MEMS for short. Electrical resonators tend to be more lossy than the mechanical due to eddy currents, resulting in the mechanical having higher quality factors. Quality factor defines how much energy does the device store versus how much energy is lost. If a resonator is kick-started at the resonance frequency, it will not oscillate forever. It has internal losses that cause the oscillation to decay. Now, using the resonator, we can ideally make an oscillator with non-decaying oscillation. To do this, we would need to compensate the losses by using a sustaining amplifier in a positive feedback. Put simply, an oscillator is built around the resonator, where the resonator selects the working frequency. The amplifier can be seen as the negative resistance or admittance that will allow the system to oscillate if its equivalent value, R negative, is greater than the losses in the resonator. We will also have to account for parasitic capacitances from the system that will essentially lower our amplifier's negative resistance. We will now look at the system's block diagram. For this chip, two oscillators were designed, both of them electrical. The first one is the LC oscillator. It is an NMOS-PMOS negative resistance topology. The resonator is in the center, where the resistance is caused by the inductor, and the frequency can be varied with the variable capacitors. The ring oscillator consists of a chain of 31 inverters, equally sized, for an oscillation frequency of around hundreds of megahertz. The outputs need to be buffered in order to drive a 15-ohm measurement setup. Since the buffers are essentially inverters, and the oscillator outputs are not guaranteed to be around half the supply voltage, these are level shifted by placing a decoupling capacitor to eliminate the DC offset, and then are offset again by half the supply voltage. This chip was designed for on-chip probing. The reason being there will be some post-processing in the future that requires the bare die, no packaging. For this, we assembled a testing setup. The setup consists of a probing station, two power supplies, an oscilloscope, and a spectrum analyzer. The probing station includes two types of probes: the DC IPass probe for biasing, and the RF GSG ground signal ground for the output of the ring oscillator, and the SGS signal ground signal for the differential output of the LC. Now let's probe the LC oscillator. For this, we will have a voltage supply for biasing the system, and one more voltage supply to vary the control voltage of the variable capacitors, effectively changing the oscillation frequency. All of these are applied to the chip through the 4-point DC IPass probe. To measure the output, we will use SGS RF probes due to the signal being differential. As we will see now, the frequency will start to change as the control voltage is slowly ramped up from 0 to 1.5 volts. Thank you for watching this video. For more background information and details about the results, please visit the class webpage.